Howdy all, welcome to a new chapter, a new unit as we go toward the end of the year. Hey, back into some algebra, we took a little detour, headed into geometry, studying shapes and how to measure those shapes. We did use some algebra in those, particularly using multi-step equations to solve problems about angle relationships. We're going to dive back into more algebra-centered concepts. Today we will be doing lesson 12-1, that's chapter 12 in our textbook, lesson 1, graph inequalities on a number line. All right, focus for the day is to do just what that title said, to graph an inequality in a number line, as well as to go the other way. Maybe instead of graphing the inequality, maybe we're given the graph and have to write the inequality. So write an inequality, graph the solutions of an inequality sooner or later. So by the way, solution, that's going to be pretty important to learn for today's stuff. And then we're going to need today's stuff to eventually solve and graph the solutions of a multi-step inequality. So pause your video, come on back when you're ready. Yes, ladies and gents, that does say assignment number 1. Usually this is about the start of the fourth corner. Now don't fret that we're a little behind. That's just the nature of this year. But that's the reason why we're doing assignment number 1. To start off, let's discuss what an inequality is. An inequality is any mathematical sentence in which two quantities, two substances, two numbers, and actually it can be more than two quantities. It's any mathematical sentence in which two or more quantities are not equivalent. Now you'll also see symbols like this and this and this and this, or the not equal symbol. Now notice I didn't read these because, well, it kind of depends on how you read them. For instance, you can read this statement as 5 is greater than 3. You can also read it going the other direction as 3 is less than 5. So keep that in mind, that you don't always read left to right, that you can read an inequality either direction, really. Solution to an inequality. Hey, listen, we've been talking about this for a while. A solution is any number or numbers that make or makes a statement true. Now notice I've been saying this since the beginning of the year, but perhaps you've been saying, well, wait a second. When is there more than one solution? When is there more than one number that makes a statement true? Ah, my friends, get ready for it. Let's begin with some vocabulary. If you do read these as left to right, in this case, you're going to say any number x which is less than or equal to, and then fill in the blank. Maybe it's 3, maybe it's 4, maybe it's 44 billion. Naturally, the next number simply means not equal to. If you read the following statement, you're going to say any number x is greater than. Notice it does not have the or equal to bar, but the one right under it does. Any number, as long as that number is greater than, or it can be equivalent, exactly the same as, whatever. And then reading this one left to right, any number x, as long as x is smaller or less than something. Those are the basic descriptions. Now let's get into the graphing, shall we? So we're going to graph the solution or solutions to the inequality on the number line. Now I want you to think about what numbers would make this statement true. The obvious one, 3 greater than 2? Yeah, that's true. So just picture a little dot there. What about 4? Yep. What about 40 billion? Yep. The truth is that there's a lot of numbers that are greater than 2. What about 3? What about 2.5? Is 2.5 greater than true? Well, absolutely, Mr. Callan. What about 2 and 1/4? Sure. What about 2 and 1 billionth? Sure. What about 2? Is 2 in fact greater than true? And the answer is no. If I were to write 2 is greater than true, you would say, that's a false statement, Mr. Callan. And you could say the same thing about 1. You could say the same thing about 0. You could say the same thing about any negative number. Those are all false statements. So we do not have any solutions off to the left. I'm going to go ahead and erase that then. Therefore, if we know all these solutions are true, and just because our graph stops at 10 doesn't mean the set of numbers does. Could be 10 trillion, could be 10 trillion, 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 and all those fractions and decimals. Therefore, ladies and gents, we're going to draw an arrow to the right of 2. But remember what we said. Is 2 greater than true? No, it is not. So we need to make sure, sorry, I don't know why I did that. We need to make sure we don't put a full dot at 2. In other words, 2 is not a solution, but every number just to the right of 2 is. We call that an empty or an open dot. And the reason it's empty is because 2 is not a solution. But even the numbers just a little to the right of that, 2.1, 2.00001, all of those would make true statements, but not precisely 2. Onward we go. Next up, we're going to ask to be graphing any solution that is less than or equal to 8. Now, obviously, you're going to say 7 is less than or equal to 8. Yep. You're going to say negative 7 is less than or equal to 8. Yep. You're going to say 0 less than or equal to 8. Yep. So I can go ahead and just kind of start that off. 7 works, 6 works, 5 works, 3.5 works, 1 1/14 works, 0 works, negative 7 works, all this stuff works. So I'm going to go ahead and use a line, excuse me, I should say array, that will go to the left forever and ever and ever and ever. After all, negative 10 trillion 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 is also less than 8. Naturally, we are not going to put any coloring over here. Is 8 less than or equal, excuse me, I did it again. Is 9 less than or equal to 8? No, that's a false statement. And you can say the same thing about 10 and 11 and all that. Hey, what about 7 and 9/10? Or 7 and 999 thousandths? Well, yes, Mr. Callan, that is less than or equal to 8. So let's put those numbers up here, huh? Last but not least, what about 8? True or false? 8 is less than or equal to 8. Well, it's not less, but is it equal? It is. This is a true statement, and therefore we would actually color in right on the 8. So instead of using an open dot, we use a solid dot. Solid as opposed to empty, closed as opposed to open. Solid or closed dots means yes, yes, yes. The number that is sitting on is in fact a solution because, for example, 8 is in fact less than or equal, because that or equal part, it makes a true statement. 8 is less than or equal to 8. Onward we go. Y is less than 3. Well, you already know what's coming. 2 works, 1 works, 0 works, -1, -2. In fact, all those fractions and decimals in between. How about 2 and 5/10? Yep, 2 and 5/10 is less than or equal to 3, even 2.9. So we're going to use array starting at the 3, going to the left. Oh, wait, Mr. Callan. True or false? 3 is less than or equal to 3. Excuse me, I just read it wrong. True or false? 3 is less than 3. False. It does not say or equal. Therefore, we're going to make sure to use an open dot so that people say, hey, what about exactly 3? No, no, no. Exactly 3 does not work. One more, -7. We want a number that's greater than or equal to -7. -6 is bigger, -5 is bigger. Hey, those numbers are not bigger, but they are better, right? I'd rather have -$5 than -7. -4, -3, -1.5, -14/77, 0, 1, 3, 5.5. All those numbers work. So if I start at -7 and I go to the right forever and ever and ever, that begins to describe the solution set. Question, true or false? -7 is greater than -7. -7 is, no, not, wait. Is -7 equal to negative? Yes, it is. Because -7 works, exactly -7 works, we're going to use a solid or a closed dot. So the green now describes all the numbers that would be true, that would make that statement true. Let's go backwards now. Let's actually start with the graph and come up with an equation, or excuse me, an inequality. X compared to 1. Well, so far it looks like all these numbers are smaller than 1, so let's go ahead and write that. Now, question, is 1 a solution? Oh, sure, 1 is a solution. It was colored in, and therefore we're going to write it can either be less than 1 or it can be equal 1. Our final answer, any number x as long as x is less than or equal to 1. This is what it'll look like if you typed it out. Onward, how about this guy? Okay, I see that it looks like it starts at a 4, so we're looking for any number. I'm just going to pick y, what the heck. No, let's stick to x. I don't care what variable you use. Looks like all these numbers are bigger than 4, even 4.5, even 4.001. A question, little disappearing ink here. Can it equal 4? No, 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 look. It is not able to be 4. Let's make that or equal symbol disappear. The only numbers that will work, any number x works as long as x is larger or greater than 4. Do not put that or equal to symbol underneath it. Let's do one more. All right, looks like we're starting at -5. We're looking for all the numbers that are, let's see here, these are smaller or less. Now, can it equal negative? Sure. Because that is a closed dot, it's either smaller than -5 or it is equal to -5. So this solution set, the colored line array, I should say, and the dot, describe all the solutions for any number that is less than or equal to -5. Last one, I do believe, looks like these are all numbers compared with -3. It looks like all these numbers are greater than -3. Can it be? It cannot be equal. So do not put that or equal to bar because 3 is not colored in. So the solution set that is graphed are all the numbers that are greater than -3. Boom, that's what I got for you, ladies and gents. Go at it, please. Page 335, number 6 through 13, all 14 to 22 evens, and 24 to 31, all. That's what I got. Let's grow. See ya.